Okay, so let me start. So the topic for my sharing today is evolved gas analysis mass spectrometry, an alternative technique to TGA, the thermogravimetric analysis, particularly to see what EGA-MS can offer compared to TGA for advanced polymer characterization. Okay, so myself, Sathrugnan working as a regional technical manager for Frontier Laboratories, and I'm located in Singapore. In next 30 minutes, I'll be giving a brief introduction about TGA and EGA, then show some data in terms of comparison for different set of polymers. Then finally, I will share some typical examples where how the evolved gas analysis can provide some additional information compared to the TGA data. I'm sure every one of you is very much familiar with thermogravimetric analysis, which is basically a tool that is widely used in material testing, and it provides the weight loss information of the material with respect to heat. Okay, so basically the TG curve represents the change of percentage weight loss with the increase of temperature. So most often we try to use the differential thermogravimetry curve, which represent the rate of mass change as a function of temperature. Okay, so basically what we get from a TG data or the DTG is basically the peak top temperature of the material. Okay, that tells the thermal stability of the material. On the other hand, evolved gas analysis is actually a kind of technique that is coupled to a GC column and mass spectrometer. Okay, so what you see here is the Frontier Lab pyrolyzer that can be connected to a GC. Okay, directly inserting the outlet needle to the inlet of the GC. Then we use a transfer tube or deactivated stainless steel capillary tube to transfer the evolved gas into the mass selective detector. So if you see the evolved gas analysis MS curve, it is almost same as the differential thermogravimetric curve, okay, TDG curve. So where we see the peak top temperature for the polymer as well as the additives that is present in the polymeric material. If you compare the data collection mode in TG, we are constantly measuring the weight of the mass, the weight of the sample in the microbalance, and we estimate the weight loss information. In EGA, we are constantly measuring the compounds that are evolved while heating the material from low temperature to high temperature. So we are not really looking into the remaining material. We are constantly looking to the compound that are evaporated during this thermal treatment. And we use a full scan range. That means we collect the compounds in the mass range of like 39 to like 500. So from this TIC, the total ion chromatogram, we can look for specific information by getting this extracted ion chromatogram and also the associated average mass spectra. Okay, so this is the difference that you get from the EGA-MS compared to TGA, because in TGA what you get is basically only the peak top temperature, and also understand the amount of volatiles, additives compound present based on the peak height of the additive zone or the volatile zone. Okay, whereas this peak intensity refers to the different compounds that are evolved during the heat process. So in summary, what I can say, the EGA must give the chemistry of this degradation pattern in addition to the thermal stability or the peak top temperature. Okay, so this slide basically shows the simple comparison. So TGA provides the TG curve and the DTG curve, which basically provide the peak top temperature of the material tested. On the other hand, EGA-MS provide a similar to this DTG, but since the data is collected through the mass spectrometer, we can also get the average mass spectrum of this peak, which can give a lot of information on the chemistry of the compound and the degradation process. So that's additional information that one can get from EGA compared to TGA. So we have compared the TGA and EGA-MS for different set of polymer. As you know, for TG analysis, we have to take around like 5 milligram, whereas EGA analysis can be performed with 0.2 milligram with a split ratio of 1/50. The reason behind this lower mass is MS is very sensitive detector. So we are able to get signal even with small sample mass. Okay. So you can compare the different polymer that are being like shown here, like the melamine formaldehyde resin, PTFE, polystyrene, and also this polyamino bismelamide, then polydimethyl siloxane, and polyvinyl chloride. So one common observation you are seeing here is the peak top temperature of TG is always observed higher than the peak top temperature of the EGA data. Okay, this is consistent with all type of polymer that we have tested, and we try to plot the peak top temperature of the two different technique. Okay, the differential thermogrametric curve, also the EGA curve, and you can see it shows a very good trend, and also the correlation is 90%. However, there is a difference of 10 degree. So the reason for this small difference in the peak top temperature is the sample amount, because as I said, in EGA analysis, we are taking 0.2 milligram, whereas in thermogrammetric analysis, we have to take 5 milligram. To demonstrate the way sample mass is actually limiting factor in this temperature difference, we have taken different mass of sample within EGA, okay, and we can see the peak top temperature is increasing even with EGA curve also. So when we take 0.136 milligram, it's around 441. When we have 5 milligram, it is already like 446, and 10 milligram 448. So it clearly shows the sample mass is one of the limiting factor, okay, due to which the thermogrammetric analysis data shows higher peak top temperature compared to the evolved gas analysis MS data. The reason for this difference is basically due to the thermodynamics, okay, where the particle size and sample mass determine the rate controlling regime. So in ideal situation, we want to use smaller mass and a smaller particle size. Okay, so that is what the Biot number versus the pyrolysis number shows. To get the best data on this peak top temperature, one has to use smaller size particles and smaller mass sample. In TG, we are not able to use smaller mass. That's why the peak top temperature in TGA is slightly higher, but it is more like a systematic error which can be corrected. Basically, we are trying to explain why this difference, which is basically due to the sample mass that is employed in these two different techniques. Now let me move on to some examples to show how the evolved gas analysis can provide more information in addition to the peak top temperature or the thermal profiling or the temperature profiling of the material. Okay, So here I have an example, okay, that is a ceramic composite material which is used in injection molding. So to understand the polymer composition of this composite material, we have analyzed by wall gas analysis, which is similar to TGA, okay. Basically, we have the starting temperature of 100 and heat up to 500 at the rate of 20 degree per minute. So based on the compounds evolved, you can see a pattern, okay. So larger the peak means more compounds released during this heating process. So each of these peak represents the compound that are evolved. So we can collect the mass spectrum of each of these peak, and we have our own database for additives and polymers, which can help you to even identify the type of polymer and additives present in this compound. Okay, so in this case, from this average mass spectrum and our library database, it shows the presence of additives like phthalate, saturated hydrocarbon, and polymer is basically a polybutyl methacrylate and polystyrene. So this is the additional information that evolved gas analysis can provide compared to the thermogravimetric analysis. Okay, I have few more examples to have some insight how the EGA is useful for product differentiation or product characterization. At the same time, we should understand EGA alone cannot really determine the complete characterization. Okay, so that is more like a preliminary step which will allow you to decide the next step of analysis, whether it is a flash pyrolysis or thermal desorption or combination. Okay, so that is very important to understand. We cannot complete the characterization part just by doing the evolved gas analysis alone. Here I show an example of this analysis of biodegradable plastic bags. Okay, so as you know, in the market now, people are trying to introduce biodegradable plastic bags, for which sometime we are paying higher price. So it's important to understand how the chemistry of these compared to the synthetic polymer bag. Okay, so we have taken two type of sample from the market that has been analyzed. Okay, so here you can see the presence of polylactic acid, okay, and also this polybutylene succinic acid co-adipate, and also the polybutylene terephthalate. So these things can be like determined based on the average mass spectrum of the different temperature zone. Okay, from this average mass spectrum, we can compare it with our database, the library database, whereby you are able to get the chemistry part of the material. Okay, so that's the key thing. So the second example is the analysis of medium density fiber board. As you know, in medium density fiber board, they are using a different type of additives to increase the strength of the material. So here we have compared two type of medium density fiber board from the market, and mostly they use urea resin and melamine resin as a additive. So we have used this as a additive material and also looked at their peak response factor with respect to the temperature. So now when we analyze the additive material, which gives a strong peak at 375, whereas when we see the MDF, the medium density fiber board from the market, they show a strong peak at 326 in both cases. Okay, but when we look at the extracted ion chromatogram, we show that it shows the presence of urea resin, and also it is showing the peak broadening, which is due to copolymerization of the fiber with the urea resin. Okay, these are the additional information that evolved gas analysis provides to understand the degradation pattern and the degradation process of the material, which will be useful for material characterization or failure analysis, or even for some of these reverse engineering applications. So the example 3 is talking about the evaluation of age deterioration of uh, polyethylene pipes. As you know, the polyethylene pipes are used for hot water circulation. So here we see the physical appearance change when the polyethylene pipe is used for hot water circulation over a period of time. So we can see there is a color change which could be due to some oxidation. Okay. Now we have taken both of these samples and have done the wall gas analysis. We can see there is a small shift in the peak top temperature. Okay, so that means the new material has got the peak top temperature of 490, whereas the used one, the deteriorated one, shows slightly lower peak top temperature. That means there is some decomposition that has happened during this hot water circulation. So we have looked into the average mass spectrum of these two material. Okay, particularly we were looking for the antioxidant that are generally added to keep the thermal stability of the material. Okay, so when we have the ergophos and ergonex as a new material, we can see the thermal stability is showing like 490, whereas as it is being used, there is a reduction which can indicate the loss of this antioxidant from the base material. So same thing can be confirmed when we look at the average mass spectrum of this ergonex and ergophos. Okay, in new material, we can see clear peak for both these antioxidant, whereas in the used polyethylene, these two compounds were not present, so that they were absent. So due to which the material degradation is starting. So the antioxidant is really helping to keep the thermal stability of the material at the beginning. As we use over a period of time, these antioxidants have been disappeared due to degradation, due to which the base material also started decoloring, also getting reduced in terms of the molecular, the weight of the material. Okay, so this type of information a wall gas analysis can provide compared to the TGA, which can only provide the peak top temperature. Okay, does not provide the chemistry changes of the material. So this is the last example again to get an idea how the EGA can help us to look at the important information even at wall gas analysis itself. So as you know, there are different type of styrene-based polymer. So we have taken different type of polymer. Okay, so like AS, AES, and ABS. So they are basically acrylonitrile-based different styrene polymer, and we create a database based on which we can look at the unknown sample. Okay, based on this principal component analysis. So the evolved gas analysis can provide this kind of information also based on just the peak top temperature as well as the average mass spectrum of the different polymer, where we identify the marker ion for different type of styrenic polymer and use it in the uh, principal component analysis. And this can be used for analyzing the unknown styrenic polymer. Okay. So I have given 4 different type of examples to show how the evolved gas analysis can provide additional information compared to the thermogravimetric analysis data. So in nutshell, we should say because the TGA and EGA both provide the temperature profiling of the material. Particularly, we can determine the peak top temperature. However, the evolved gas analysis can provide additional information based on the chemical changes that has occurred during this thermal treatment. Okay, so The take-home message: a chemical characterization should be integral part of advanced material characterization because it provides a functional and performance characteristic of the material. And pyrolysis GCMS, as we have listened to the previous talk, where they have shown the use of pyrolysis GCMS to understand even uh, the photo-oxidation characteristic of the aging polypropylene based material. So basically the PYGCMS can be operated in different mode like evolved gas analysis, thermal desorption, or like flash evaporation or pyrolysis. So by combination of these different techniques, we can extract as much as the chemical information of the material, which will allow us to understand the characteristic of the material to decide its suitability for different applications. Similarly, it provides an important part in failure analysis as well as the reverse engineering application when a researcher is trying to develop a new material based on their competitor products. Okay, so with that, I would stop here. If there are